right. So I said there are two ways in which we can build linear classifiers. So one was the discriminant function approach, right, where by comparing discriminant functions we decide what is the separating hyperplane, right, and what is the other approach? Modeling the separating hyperplane directly. Right. So there are many ways in which this can be done, and we will look at two in particular. One because it leads us into neural networks later, the other because it is the most popular way of building classifiers nowadays. Okay. Before we go on, let us just have a little fundamentals again. Okay. So that is a separating hyperplane, right, and right. So this constitutes of all points x such that this equation is satisfied. Okay. So this is a definition of a separating hyperplane. So I am going to call f of x equal right, that defines our hyperplane. If we equate f of x to 0, that defines our hyperplane, and if f of x is whatever, right. If it is greater than 0, it implies in this case g of x is 0, right. So some properties here. If x1 and x2 both belong to the line, okay, I am just going to call this L. If x1 and x2 both belong to L, then we know that beta transpose x1 minus x2 will be 0, right. So what does it mean? The beta is actually a normal to L, right. So beta is normal to L. Right, so I am going to assume a specific, actually okay, beta star is normal to L, beta is perpendicular to L, okay. So beta star is a normal, is unit direction, I mean unit dimension. Okay, this also we know. So beta transpose x naught equal to minus beta naught, right. So I mean that essentially gives you this is 1 minus beta naught, that is plus beta naught, so it will be 0, okay. This is beta, remember the beta naught is left out here, okay. So beta transpose x1 will be minus beta naught, beta transpose x2 will be minus beta naught again, so this expression will become 0, that is why x1 x2 belong to L, if people have not thought about that. So what is that? This is beta star transpose x minus x naught, where x naught belongs to L, x does not belong to L. What is that? Beta star naught is a direction that is perpendicular to L. So, this is essentially the distance of x from L, right. It is actually the signed distance of x from L, depending on which side of L it is, this is going to be different, but because I am multiplying with beta star, it gives me the projection on the perpendicular. So, this gives me the distance to L, right. Some x, right, and this will be the direction of beta star, right. So, this is essentially projecting that onto this direction. So, this will give me the okay. Right. So, beta star we know is beta by norm beta, right. So, I replace that. So, I get beta transpose x plus beta naught, because x naught times beta is minus beta naught. So, I get plus beta naught. So, and this expression is actually f of x, right. So, this is f of x divided by norm beta, and beta is what? F dash of x, right. If I take the derivative of f of x with respect to x, it gives me beta, right. So, essentially, so it is norm of f dash of x, right. So, this is f of x divided by the norm of f dash of x. So, what did we say this expression was? The signed distance to the hyperplane. So, f of x gives me a quantity that is proportional to the signed distance to the hyperplane, right. And if I find a hyperplane such that I normalize my beta to be 1, f of x gives me the signed distance to the hyperplane. It is not proportional, it actually gives me the signed distance to the hyperplane. Okay, that makes sense? Yes, I just want you to keep this in mind, because whenever I say I am going to minimize f of x, it essentially means I am going to try and minimize the distance of the data points to the hyperplane, or when I am going to say I am maximizing f of x, I am going to maximize the distance of the data point to the hyperplane, right. So, just to keep that clear, I am just introducing these notations beginning. So, the first thing we will look at is a perceptron learning algorithm. So, it has got a hoary tradition, right. People are familiar with, have heard the term neural networks, artificial neural networks? Yes, no? People have heard the term artificial neural networks? So, you know that we are going through the third boom of artificial neural networks, okay. So, back in the 50s and 60s, there was this initial boom of artificial neural networks, right. Everybody was so taken up with artificial neural networks. They said, oh, here is something that can solve the human learning problem. Did we talk about this already? Yes. Right. So, that was started by the perceptron learning algorithm, right. And what about the second boom? People know what the second boom was? Okay. Yeah, we will come to that later. Right? So, the second boom was started by the back propagation algorithm, which took care of some of the problems with perceptrons, and then that also died away, and the third boom has been started by what people call deep learning now, right, and the hype is scary. But apparently not as scary as it was. I mean, I recently read some newspaper clippings from the 60s. It is really scary. Okay, yeah. So the idea behind the perceptron learning algorithm is very simple. Okay, so I have this decision boundary, right? I want to make sure that any point that I actually misclassify, right, any point that I misclassify is as close as possible to the decision boundary, right. In fact, if I put it on the other side, I am happy, right. I am doing the sign distances, right. So if I put it on the right side, I am happy, right. If you put it on the wrong side, well, I try to keep it as close to the hyperplane as possible, so that, well, at least there is some kind of satisfaction that we are not getting something very egregiously wrong, right. So I am going to minimize right. So we will assume that for data points which is such that xi beta plus beta naught is greater than 0, I will output as class plus 1, right. Whenever it is less than 0, I will output the class as minus 1. So if the true class label is plus 1, but if the f of x is less than 0, I mean f of x is less than 0, that means I will be outputting minus 1, right, but the true class is plus 1, so that means this has been misclassified, right. So likewise, if right, does that make sense? People have to understand this point now, right. So if the true class was plus 1, but f of x is less than 0, then x will get misclassified, right. The true class was minus 1 and f of x is greater than 0, then x will get misclassified. So these are the two conditions under which you will have a point being misclassified. So if I take this quantity, right, so what will it be for misclassified points? It will be negative for misclassified points, it will be positive for correctly classified points, right. I take that and I minimize it, right, for all so take this for all the misclassified points, right, and I try to minimize this. So D is sometimes called the perceptron criterion, right, or the perceptron objective function, okay, right. Does it make sense what we are trying to do here? Louder. Right. Okay, I will try to write bigger, but the idea was that that gives you zoomed in thing. If I am very small, then I will try to write bigger. Yeah. Okay. So the point here is that I will not rewrite this, from subsequently I will write bigger. Okay. Point here is that if you take the misclassified data points, okay, so this is going to be a negative quantity, right, and I want this to be as close to 0 as possible, right. In fact, I want M to be empty, right, I want M to be empty. Okay, so that is the goal. Okay, so the way to minimize this is to make sure that M is empty. As long as M is non-empty, right, I still not achieved the optimum. Okay. When can M become empty? Huh? So if my data is actually linearly separable, right. If you remember, earlier I drew some data points sampling from Gaussians there, right. I drew a minus somewhere here and then pluses there and so on and so forth. That kind of a data will never be linearly separable. I can never draw a straight line separating those data points, right. So here things are nicely linearly separable, right, all the x's are one side, all the zeros are on the other side, right. Here the data was nicely separable. So the perceptron objective function works well if the data is linearly separable. If it is not linearly separable, we will run into problems. Okay. Great. So now what we do is just use gradient descent. So I will find rho d by, so what will that be? Okay. Font sizes are fine. Okay, good. Right. So this is the derivatives, and then so what I do now is essentially, this is a technique that is very popular nowadays, but it was not really called by that name in the olden days. So it is called stochastic gradient descent. Okay. So people know what gradient descent is. Yes, what is gradient descent? Huh? Yeah, usually you find the direction of steepest ascent and go in the opposite direction. Yeah. How far do you go in the opposite direction? Proportional to the what? Proportional to the gradient. So the gradient is very large, then what do you do?
Based on the iteration in which we are doing.
Right. So it depends, right. So if you know the gradient properly, I can compute the gradient, set it equal to 0, solve for it, right, and then just jump there, right. I do not have to go in small steps. If I actually know where the gradient becomes 0, I can just set my solution to that point, right. So the problem comes when things are a little iffy. Why? As soon as I move my beta in some direction, what will happen in the perceptron case? If I move my beta, right, so if I move in the direction of the gradient, what will happen? Set M changes, right. So immediately my definition of gradient changes, right. So when I change beta slightly, I will have to recompute the gradient, right. So the gradient I am computing is valid for wherever I am sitting in the beta space, right. When I move from there, then I have to recompute the gradient. So I can't just move in the direction all the way, right. I can't really move a long distance pointed to by that particular point in space, right, particular gradient. So I have to iteratively recompute the gradient, right. So in such cases, what we do is usually take a step in the direction indicated by the gradient and hope that you are moving in the general expected direction, right. So if you take the expectation of the gradient, you are moving in the right direction, right. So the stochastic gradient descent has a lot of nuances and other things to it. So we will not get into that. Whenever we use stochastic gradient, I will point out to you, okay, what are the things to be concerned about. but we will not get into details of that, right. Possibly anyone doing the optimization course, and yeah, you might, I am not sure whether they are going to get to stochastic gradient descent, but they might cover it in that course, but not here, right. So what we are going to do is essentially take beta right. So the gradient is xi yi, right, but since I am anyway doing stochastic gradient, right, as soon as I find one misclassified data point, I am going to find the estimate of the gradient and move in that direction. I am not going to wait till I find all the misclassified data points under that particular beta, right. For the current beta, I will find one misclassified data point and then I will change my beta in the direction of the gradient, right. So what does it look like? So I just take the misclassified data point, multiply it by the desired output and add it to the weight vector, right. I have written this in a really funny spacing, right. That is because I can lazily, what should go here? Now I can convert this into matrix notation, right. So every time I encounter a misclassified data point, I change my beta, right. So we are doing it in this particular form because this is the perceptron learning algorithm, right. So if you want to find all the misclassified data points and then compute the cumulative gradient and then change your beta in that direction, you are welcome to, okay, that is a perfectly valid way of doing it, okay. The reason we are doing it one data point at a time is this is exactly how the perceptron learning algorithm was derived. Yeah.
How do you get that weight?
Which weight? Okay. So rho has to be really small if you are operating in a very stochastic environment, okay, because so in effect what you are doing when you are doing stochastic gradient descent is that you are making many different estimates of the gradient in a local region, right, and you are trying to move in the expected direction, the average direction of the gradient. So if the rho is very large, okay, it turns out that you will just make one estimate of the gradient and then move out of the region, right. So you will take a large step, so you will go somewhere else, the gradient will be completely different, right, or this could have been the wrong estimate for the gradient direction. So to make sure that you are following a reasonable expected gradient, rho has to be really small, okay. Having said that, in the perceptron learning algorithm, setting rho to 1 actually works, okay, and that is how the original perceptron algorithm was also stated, right, rho was 1, and normally for stochastic gradient descent 1 is very large, okay. You typically think of the order of 10 power minus 3, 10 power minus 4 and things like that for step sizes, okay, but it turns out in this case it is fine, right, rho equal to 1 is fine and it will work, it will converge, you can show convergence with rho equal to 1, but if typically in stochastic gradient descent you want rho to be really small because the idea is what I told you, just like we talked about taking replacing expectation with an average over a region when you do nearest neighbors, so something like that, okay, at a very gross level. So you want to be able to take an average of the gradient in the local region, but if you move very fast then you might be in a completely wrong direction, okay. So therefore you go slowly, okay. Great. So this is the perceptron learning algorithm. Yeah.
What does beta L stand?
Beta?
L.
Where is beta L? Sorry about that, and that is not beta j either. Right. So if the data is linearly separable, so what do you mean by linearly separable? That there exists a linear separating hyperplane that will make no mistakes, okay. So if the data is linearly separable, then the perceptron algorithm learning algorithm will converge to some solution, okay. So what do I mean by some solution? So here we saw, okay, let me do it again. Right. So let us say these are the data points that are given to you. Right. There are many solutions that work, right. Right. I mean, assuming all of those are straight lines. So you have many different straight lines that you can draw that separates these two classes, right, infinite number of them actually, correct. So the perceptron learning algorithm will converge to one of these three or one of these many infinitely many number of separating hyperplanes. Which one would it converge to? Depends on the starting point, but it is hard to say a priori, right. Given a starting point, can you tell me what is the hyperplane is going to converge to? You can, just have to run the perceptron algorithm, yeah. Yeah, sorry. Yeah, you are going to say something. We will come to that, okay. There is a way of defining one of these infinite number of hyperplanes as the most desired hyperplane, okay. So if you think there is a way to pick one of these, yes, we will come to that, okay. The second problem is it can take a long time. It can take a long time, especially if the gap between the two classes is very small. And if the gap between the two classes is very small, then it can take a long time, okay. So partly it is a function of setting rho to 1, but then it's hard. I mean, so see, setting rho to 1 essentially makes your thing oscillate a little bit, right. So you will have something that makes a mistake here, then you will go back, you will make a mistake here, and then you have to keep going back and forth multiple times before you converge to the right answer. But then setting rho to something small, okay, will also make you move only small steps at a time, so that also may take a long time. So there is always a trade off between how large you make rho and how small you make rho, right. And so one way of fixing this is what?
After some point of time, reducing
Rho proportion.
Rho is one thing, but can you increase the gap between the data points somehow? Transformations, use basis expansions that we talked about earlier. So instead of doing it in the original x space, say do it in the x squared space or 3x space or whatever. I mean, you can think of some way of scaling the data or transforming the data so that the gap between the classes is widened and therefore it converges quicker, right. But the third problem is the harder one. The data is not linearly separable, what will happen to the perceptron algorithm? Right, there will be no hyperplane where M is empty. So if, as long as M is not empty, I am going to keep adding something to the beta again and again, right. As long as M is not empty, I will keep adding data points, every iteration I will be changing the beta, right. If not linearly separable, then it enters or that, okay, then it loops basically, then it loops. But the problem is sometimes the loops can be very large, right. If you have a very large data set, right, it might actually be setting up a very large loop, so it may not be easy to detect also, right. So normally it takes a long time to converge, right. In that, if it is looping, so you have no way, you do not know if the algorithm is taking a long time to converge or whether it is simply looping. So how could you detect loops?
cardinality of n.
Huh?
Cardinality of n.
So you think that every time it has to monotonically decrease? If it is going to converge, yes, right, you think so, right, towards convergence, yes, but when it is taking this whole bloody long time to actually work through the thing, right, so there is no guarantee that cardinality MF will monotonically decrease also, right. So it is not very easy, okay, cardinality MF is not the only thing that will give you, so it is yeah, there is no efficient way to get around that, okay. So the problem is yeah, so people discovered a lot of drawbacks to perceptrons, and the biggest drawback was they discovered that some very simple problems that you want to solve are not linearly separable, right. So XOR, that is XOR, right. So XOR is not linearly separable. I simply can't even solve simple problems like XOR. What a useless thing is. I don't care how well you make the baby speak, you can't solve XOR, so I am going to forget about. People remember I gave you the example how they trained a perceptron to reproduce speech, and as the training progressed it just sounded like a baby learning to speak, and people just went gaga over it, you know. Anyway, so we will stop here, looks like I am actually out of time. So next class we will try to look up we will try to explore a way of fixing this, right. So what is the problem there? Not that it is linearly separable, but the fact that it could converge to any solution that is linearly separable. We will start by trying to define a single optimal solution.